Okay, so this will be the third online lecture for ECE 341. Last time we were talking about multiple random variables. We approached that topic by looking at a pair of random variables. We looked at this thing called the joint CDF. That turns out to be a little awkward to work with, so we moved down to what is called the joint probability mass function, dealt just with the discrete time random variable case, and also looked at a connected concept called the marginal probability mass functions. Those are probability mass functions of single variables, something we'd seen before, but obtained through the joint probability mass functions by summing out the variable of non-interest. Today, we're going to just look at the continuous random variable side of this and look at something called the joint probability density function. We can also look at the marginal probability density functions, which can be gotten from that joint probability density function. In presenting this joint probability density function idea, we'll take a pretty large example and make sure that we can work our way through it and see where we can get with it. So let's talk about this idea of a joint probability density function, so a joint PDF. This is a probability density function that is really much like what we've studied before, just now as a function of two variables. In this particular case, I'm going to let the variables be x and y. So I have a little f of xy of the observations, little xy. And this probability density function has the typical kinds of properties we'd expect with a probability density function. One of the things we can do is we can connect it to the joint CDF, which we've already looked at before. We know the joint CDF, f of xy of little x, little y, right, is just an accumulation of probability. And we can accumulate that probability by integrating over a part of the xy plane, the probability density function, the joint probability density function. So it's an accumulation from minus infinity to x, and it's an accumulation from minus infinity to y, right, of my probability density function fxy. I'm going to give myself some variables of integration, so I'm going to call those u and v, so I don't confuse them with the x and y that are in the limits of integration. And here, because I'm doing y first, and I called yv, I get a dv and I get a du after that. So it's a nested integration. It's a double integration. We could be completely equivalent in doing this in the other order. We could integrate this from minus infinity to y and go from minus infinity to x and have that same probability density function fxy u comma v, but now because of the order of integration, I would get a du dv in that particular case. Either one of these should work. There's matters of convenience or geometry that will oftentimes suggest one order of integration is better than the other. We'll certainly see that in the example that we do. So probability density function, just like in the univariate case, can be used to get the accumulated distribution, the CDF, through integration. And we just integrate, in this case, in a two-dimensional area, right, in the xy plane rather than on a real number line. Of course, we could also just get the probability density function, this joint probability function, fxy of little xy, through differentiation of the CDF. Now, because it's a function of two variables, we're going to do this as a second partial, the first one with respect to, let's say, x, the second one with respect to y, and then we just put in our CDF, fxy of little xy, something along those lines. Of course, we could also write this out as completely equivalent, as you know from calculus. This is the second partial with respect to y and with respect to x of fxy xy. Either one of those would do it. So you can differentiate, right, the CDF to get the probability density function, the joint probability density function, or you can integrate the joint probability density function to get the joint CDF. The probability density function here, just like any old probability density function, has the basic probability density function properties. So f of xy, little x, little y, has to be greater than or equal to 0, right? We can't have negative distribution or negative density of probability. So what does this translate to, or how is this connected? Really, this is a consequence since our f, our joint CDF, which we had introduced last time, and its properties is non-decreasing. It's a non-decreasing function. Since it's a non-decreasing function, when you differentiate it, you end up getting the probability density functions as being non-negative, which is totally sensible. We wouldn't think of having a negative probability density, you integrate that, you would get negative probability, which just doesn't make any sense. That violates our basic axioms of probability. I can also take an integral from minus infinity to not x, but to infinity. Do that twice over in both the x and y directions, and we could have our probability density function fxy, call that of a uv, however you want to do it, and we could do this du or dv, and we know that we can interchange the order there. Doesn't matter, it doesn't make any bit of difference in here. If I integrate over the entire xy plane, well, the sum probability should be equal to 1. So these are just the basic kind of properties that we've become very well acquainted with when it comes to a probability density function. We can, just like we had talked about before, when it comes to probability densities, that probabilities of individual points don't really generally make sense because we have a continuum of points that we are covering. That's why we use a density function. In the same way, we are not interested for the joint distribution in individual points or even lines of probability. We're interested in areas. So we're going to go over patches in the xy plane in order to figure out probabilities of being on intervals in both x and y. That describes things like rectangles in the xy plane. So there's a theorem in the book, and it talks about the probability, for example, that x, the random variable x, is between some value x1 and x2, something like that, and that I'm going to go ahead and let the random variable y be between a value y1 and y2. So I'm looking for the probability that x is less than or equal to little x2 but greater than x1, and the probability that y is less than or equal to y2 but greater than y1. If I wanted to think about that, I could certainly do it in several ways. We'll look at a couple. First, I'd like to get a sketch of what this thing looks like in the xy plane. So I'm going to just go ahead and put in my axes here. I'm going to have to make some assumptions since I'm writing my axis in here, but we'll go ahead and do that. I'm going to assume that I've got some value x1. x1 should be less than x2, otherwise it's not making much sense. I've got x1, x2, and that's on my x-axis. And I could also look on the vertical, which I'm going to call my y-axis, and there would be some y1, which is a value less than y2. So what am I looking at trying to figure out? I'm trying to find, right, the likelihood that I'm in this little rectangular area, something along those lines. So I know that the probability density function tells me how probability is distributed over this area, right? And so I'd want to double integrate over that area in order to find the accumulated probability of being in that patch. So if I'm interested in this particular case of finding the probability of being over those intervals, right, I'm trying to find that green area that I've just sketched in. One way of doing it, of course, if I go back up a little bit, I'm going to get a little tired of drawing that full probability piece out. So let's just call this probability of some event A, where A is being on those intervals in x from x1 to x2 and y from y1 to y2, something like that. So PA, one way of getting it, right, is just by a direct double integration. And that direct double integration would do something like going from x1 to x2 and from y1 to y2, and then I'd have my little fxy of something like what? U and v, and then in this particular case, because the integral on the inside, the thing I'm integrating first is with respect to the y variable, that's the v. This is a dv ordering and then a du ordering, something along those lines. I could certainly interchange those du dv elements, but that would require me to interchange the order of the integration outside as well. I'm integrating over a nice straight rectangular place, certainly one way of doing that. Turns out, though, that there's another way we can do this, and this isn't all that difficult to do. If you remember back to the univariate case, we could get the probability of being over an interval as a difference in CDF values. We can do something very similar here for the two-dimensional case. We've just got to be a little tiny bit more careful. Let me go ahead and draw it out as an equation, and then we're going to come back and make sure that it makes sense, at least pictorially. So we're still looking for that probability A, which is x being on the interval x1 to x2, and y is being on that interval y1 to y2. And that probability A, I'm going to put it in terms of the joint CDF functions. That could be like f of xy, and I'm going to say that is going to be of x2, y2. I'm going to subtract that, f of xy of x2, y1. And I'm going to subtract from that fxy, and I'm going to have an x1, y2. And then I'm going to make a final term in here plus some fxy of x1, y1. All right, so let's see if we can believe this equation. It's a little more complicated than what we saw for just a univariate single interval, right? We've got double intervals here, and we get 4 terms, and we just want to make sure that we can get some sense of this guy. We know from before, right, that the area we wanted, right, was that area that I've shaded in green, and that shaded area in green is corresponding to probability A once we've integrated over it. So what does this first term give us? This f of x, y, x2, y2. The CDF tells us basically the accumulated probability up to the point, in this case, x2, y2. So where's point x2, y2? x2, y2 is in that upper right corner, right, of the interval or area that I want. The CDF says take everything below that and take everything to the left of that, and we're going to include all of that probability. So at least for this first piece, right, I end up, if I look at this term right here, I'm going to be expressing that with this shaded thing with a red crosshatch, something along those lines. Clearly, we've counted too much here, right? That cross-hatched red area is much bigger than the green area, so we need to get rid of some of the stuff that we shouldn't have counted, and some of these other terms are going to come into play there. So let me go ahead and change the color here. I'm going to make this guy blue, and I'm going to look at this next term, and so I've got fxy of x2, y1. This is the accumulated probability at point x2, y1. So let's find the point x2, y1. So here is x2 and y1, something along those lines. And we are trying to take a look at what the CDF value of that is. CDF says let's look below it, right? And let's look to the left of it. And let's go ahead and figure out what that area is. And when we take a look at that, what I've managed to do is I've got rid of a lot of that cross-hatched red that I really didn't need in order to get that green area, right? So in this particular case, I've got this guy going a little bit cross-hatched to blue, something along those lines. And if I look at the combination of those two, right, what I'm left with is the green area plus a little bit of stuff off to the left of the green area. I still need to get rid of that as well. So I'm going to go to the third problem the component in here. This is the fxy, x1, y2. I'm going to do it in the same color. I'm just going to make the cross hatches maybe go in the other direction, something like that. And we'll see what we can do within that. So this one is the accumulated area at x1, y2. So I'm going to go ahead and find x1, y2. There it is. The CDF says look down and look to the left, something like that. And we said we were going to cross hatch in the other direction. So I'm going to do something like this. So I got rid of that as well. Now I'm going to have to do a little bit of maybe more shading in this particular case. Let's see if I can get some of this accounted for. The first term, fxy, this guy right here, right, got me everything to the left of x2 and below y1. That included the green area and a bunch of extra stuff. When I looked at the next term in there, this fxy of x2, y1, I subtracted off that one piece that I showed in the crosshatch blue. Same sort of thing for this other guy, right? And so what did we end up doing? We ended up getting rid of all of this stuff in one case, right? And then I got rid of all of this stuff in the other case. And what I get out of this is that I got rid of most of the stuff I needed to get rid of, but I double got rid of this piece right here, right? This piece got double subtracted out. So that actually is a problem. We only needed to get rid of it once, and we ended up getting rid of it twice, and that's going to explain this final term over here. This final term re-adds in that part that we double got rid of. So in order to just end up with the final value, that PA, which is that green shaded area, I need to re-add in this other chunk that I'm sketching in kind of a deep red, because those other two pieces that I had ended up subtracting that out one time too many. And so, of course, that is exactly what that other term does. And so if I just go and remind myself of fxy, x1, y1, something along those lines, the x1, y1 point is right here. We're looking down and to the left of that. And when we think about what the CDF, it takes all that area, which I've just cross-hatched in black, which aligns with that dark shaded red, which was the thing that we had subtracted one time too many. So I add it back in, which is why we have a plus sign there. So just like in the univariate case, we can use CDFs to help us find probabilities in areas. This is useful if I have the CDF, right? It can save us some integration. Okay, so let's transition a little bit and do some practice. So we'll pick a pretty significant example here, but some practice in trying to find probabilities over particular areas in these joint probability density kind of spaces. So let's try this. Given some event A, we've already hinted at this, some event, let's call it A, right? Then we know that the probability of A is equal to what? We integrate over whatever describes A. So I'm going to show that double integral with an A underneath it. Just means you set up your limits of integration in such a way that you cover the area corresponding to A. And then we take our joint probability density, fxy, right? And we could do this as a function of x and y. I think the book just does it as x and y. You might use dummy variables of integration, and you could have a dx or a dy or a dy or dx. So we can interchange that order of integration. Either order is okay. Sometimes a particular ordering just turns out to be a lot simpler than the other. So we kind of had an idea of this before. I've just formalized the equations on that. Let's do an example of showing this guy in play. So this is an example, and this particular example is similar. It's similar to an example in the book. I think it's 5.8, something like that. And we're going to just describe a joint probability density function. fxy, little xy, is being equal to, let's let it be a constant. So this is like a uniform random variable, a uniform pair of random variables. It's going to be uniform over, let's let it be 0 less than or equal to 2x, less than or equal to y, less than or equal to 2, and 0 otherwise. So it's uniform, but it's uniform sort of over a little bit of a strange description there. 0 less than or equal to 2x, less than or equal to y, less than or equal to 2. These joint descriptions can get a little bit complicated. So we've got a basic description there. We want to know what we want to find out. So let's first find that value c such that fxy is valid, right? So we'd like to go ahead and find out what is the value of the density function for this joint distribution fxy. And then I'm going to go ahead and do b. I'd like to find the CDF of this guy. So I'm going to find cap fxy of little xy. We know that cap fxy should be something that involves integration of that joint probability density function. Okay, well, for us to answer the first part, I do think that we need to get some sort of visual, some sort of picture going along for this joint probability density function. So let me go ahead and draw a little bit in the xy plane here. So I'm going to go ahead and draw some xy description here. So I'm going to take a look at and let x be on the horizontal axis and y be on the vertical axis. And I just want to get an understanding of the range space, right, where this probability density function is non-zero. So the range space Sxy is some place or some region in the xy plane for which we get some probability. In this case, we're going to get some probability C. And we know that that is described by this condition over here. So let's work with this. The first thing I see is that the condition 0 less than or equal to 2x has to be held true. That tells me, if I divide both sides by 2, that x has to be greater than 0. So I do know that x has to be greater than 0. So I'm going to be pointing to the right of 0. We know that. That has to be true. One of the other things that we can see in there is that y, right, has to be less than 2. And y also has to be greater than 0. Both of those conditions are built in here. So I can tell for one thing that y has to be greater than 0, right? And it has to be like less than 2. So it has to be less than 2. So that actually, if I just drew some lines in here, right, it tells me that everything that is interesting about xy has to be in that little strip in the y plane between 0 and 2. If I continue taking a look at this thing as well, I could also say that 2x has to be less than 2. That is x less than 1. So we knew x had to be greater than 0, but it's also got to be less than 1. So let's just clean this guy up a little bit. And so we know x certainly has to be on that interval there. I can draw a line in there. And that tells me that at least so far as I've got it figured out, the interesting parts of x and y have to fit in this little rectangle that is 0 to 1 on x and 0 to 2 on y. I haven't taken care of every condition. There's one final condition here in the middle, and that is that 2x has to be less than or equal to y, so I need to figure that out. Let's take a look at the equality condition of that. So the equality condition is the boundary 2x equaling y, and so that's the equation of a straight line that intercepts the origin. If you look at it, that's if you write it in maybe just a little more standard way, y equals 2x. It's a straight line, right? And it's got a slope 2 associated with as we move on x, and so I can certainly draw that line in here. So here I'm drawing in the line, right? That line there, if I look at that, is y equaling 2x. That's part of the boundary in that expression up here that tells me something about the region for which this probability density function is C. So I've got y equaling 2x there. So this is telling me that this probability density function is going to be triangular rather than rectangular, because I've got to be on one side of the line or the other. What was the condition? The condition was 2x needs to be less than or equal to y. So that's going to be one side or the other of this. It's either going to be this stuff above or it's going to be this stuff below. How do I know which one? Well, just pick a point that you can check whether this equality or inequality holds. So one of the things I might do is I might just pick either one of these two corners in here, either of these two corners that's on one side or other of that line, and see which one actually holds true. Let's take this lower right one first. What is that value? That is y equaling 0, x equaling 1. Put those values into there and see how it works. So 2 times 1, is it less than or equal to 0? No way. It is not having anything where 2 is less than 0. So I know that I chose poorly. I'm on the wrong side of that line. We could go to the other one up here. This was at value what? X equaling 0 and y equaling 2. How does that work in that particular equation? Well, I would have 2 times 0 is 0. Is 0 less than or equal to 2? You bet. I'm on the right side of the line. And what that tells me now is that if I was looking at this overall condition, 2x less than or equal to y, I'm looking to the above portion of that line I just drew. Put it in with all the other conditions, and I end up getting the region of support for this particular probability density function as being this little triangle, right? That triangle that is described by x going from 0 to 1, y going from 0 to 2, and being on the above side of the line, right? Y equaling 2x. So doing these kinds of sketches, sketching out the region of support for these probability density functions is going to be really, really critical for us in order to be able to proceed in smart ways in computing out overall probabilities. So let's go ahead and take that knowledge now. I'm going to just clean this up a little tiny bit. I know that the region of support for this particular guy, right? If I take a look at my xy plane again here, so I had x and I had y. Y got up as large as 2, x got large as 1, something like that. And then the place where this CDF, or the probability density function, is non-zero is over that triangular region. And not only that, the fxy, right, is equal to a constant on that part. So if I want to figure out what is the constant value, what do I know? I know that if I double integrate fxy, right, which in this case is going to be double integrate, right, fxy is just a constant, that has to be equal to 1. In this particular case, then, we're just talking the area of that triangle. I could do the calculus. I'm not going to do the calculus here because it's just so easy. I have a triangle of width 1, and I have a triangle of height 2, and because it's a triangle, we just multiply that width times height by a half, right? And that ends up giving me the overall area of that triangle. So this is the area of the triangle. That is equal to 1. So the area was already equal to 1, and what that tells me, because C just scaled the area, is that tells me that C had better be equal to 1. That's the only way that I would end up getting a 1 out of this. Area times the overall size of C is what this says. The double integral is the area of scaled by a value C, something along those lines. So I did get part A done on this. I know that C equals 1. I actually worked that out, so we don't have to mess with that C parameter as we go forward. Now we just have to worry about the B part, right, which is trying to find the CDF of this probability density function. Again, I think maybe just a little bit of cleanup here is going to be worthwhile. So I'm going to just remind us what we've got. Let's go ahead and go back to a black pencil. And so we're going to say my fxy of little xy, right, is equal to, in this case, it's going to be 1 for 0 less than or equal to 2x less than or equal to y less than or equal to 2, I think is what we had. Let's go back and just check that. So 0 less than or equal to 2x less than or equal to y less than or equal to 2 looks good. And then we had now a 0 otherwise. And if I did just a very brief sketch of this guy, right, we could do a very quick sketch in the xy plane. We know we can go up 1, 2 in the y and over 1 in the x, and that there's a triangle here that describes this guy, and over that triangle, right, we have fxy equaling 1, something along those lines. Now we want to find the CDF. So B, we're trying to find that CDF cap fxy of xy. This turns out to be not trivial. It's not a trivial type of calculation. There's several things that we end up having to do in this particular case. We need to do multiple different double integrals because the way the CDF intersects this area, this region of support for little fxy, is different depending on where we are in the xy plane. I think I can best show this through some pictures, but this finding fxy, xy, we will find involves what are called multiple regions, multiple regions. It's going to require multiple different calculations. There's different descriptions for fxy depending on being in different parts of the xy plane. Let's do the first region, and it turns out, just because I know where I'm going, there are 5 regions in this case, 5 regions in this case, and you'll see where this comes out as we go through. Let's look as a first region as the following. I'm going to look at x being less than 0 or y being less than 0. And I am looking for then what is the CDF fxy, little xy, for this condition, little x being less than 0 or little y being less than 0. Sketches again here are going to be really, really helpful. So I'm going to go ahead and write in my xy plane. So I have x on the horizontal, I have y on the vertical. I'm going to show the region of support as to what fxy has. So we've got this triangle that we had seen before, right? And I'm looking at a condition here now that says y is less than 0 or x is less than 0. What does that involve? That involves being anywhere over here in quadrant 2, right? Or quadrant 3 or quadrant 4. Any point there is described by that condition, x less than 0 or y less than 0. Why does that constitute a region? Let's take a particular point, or we'll take multiple such points. Let's take one over here in quadrant 2. If I took a point in quadrant 2, this particular one has x less than 0. Y is not less than 0, but we've got the x less than 0, and that was enough for us to be in this first region. And I'm interested in what the CDF might look like. CDF says look down and look to the left and see how much stuff accumulated. Well, none of that has hit my region of support for fxy, so I know it's going to be 0. If I picked a point over here in quadrant 4, same story. If I look down and to the left, none of it hits that triangle. And if I pick quadrant 3, right, same story. Everything down and everything to the left, none of these guys can intersect or hit that triangle. So this first region that I've chosen, x less than 0, y less than 0, is all the points, right, in the xy plane for which if I look to the left and down, right, we don't intersect that sx y, that region of support for my variable pair x and y. So I know that the CDF is going to be integrating a bunch of 0, which gives me 0. We end up getting 0 in this particular case. So far, so good. Heck, we're in some respects 3/4 done, right? We've covered 3/4 of the xy plane, and what we found is that this guy is 0 for all of that. Things get a little more complicated as we move forward. So let's pick a second region now, somewhere where we are going to get something non-zero. I want to look at a point of my CDF that is in the interior of my region of support x and y. So we had already had that described above when we described our probability density function, the joint probability density function. And this is a condition, what we have, 0 less than or equal to 2x less than or equal to y less than or equal to 2. We know exactly what that describes. So if I look at my xy plane, we had already looked at that. Here's xy plane. We come up 1 and 2 for my y, 1 over for x, and we get this little triangular region, right? This particular condition now, 0 less than or equal to 2x less than y less than 2, describes this little triangular region right here. And it turns out that the CDF for this particular triangular region has a particular form. Let's go ahead and see if we can draw it out. I have a feeling in this particular case I'm going to want to make my picture a little bigger, so I'm going to do that now rather than later. So let's go ahead and redraw that just a little bit larger. So I'm going to just focus more on that triangular piece. And so we're going to come over here and draw it at a larger scale, something like this. Make sure that I've got that guy going on in there. And we're picking some point on the interior of that corresponds to that condition in there. The CDF says what again? It says let's look down, right? And let's look to the left. And we need to be able to find how much probability has accumulated. So we're going to be integrating over all of this space, both to the left and below that point. Now, there's only a little bit of that region that matters, because there's only a little bit of that region that hits non-zero probability density. And it turns out to be an area that, right, looks like this trapezoid piece in there. I'm actually going to erase that. I think I'm going to undo that, and I'm going to do it instead as a kind of a green area. So we're looking for this green area in here. And it always looks like that piece, no matter what point, that black dot, you pick on the interior of that triangle. If you look to the left and below it, you're always going to get this trapezoidal shape. So what am I still trying to do? I'm still trying to find fxy for this. So I'm looking for cap fxy over this region too of little xy, right? And I know it's going to involve some integration. So I'm going to have a double integral in there. I know the thing I'm integrating is the probability density function, which is 1. So I've got all that part. Everything that makes this a challenge is being able to set up the rest of the integral, right? I need to figure out, how do I integrate that little trapezoidal shape? There are two options that I have in this particular case, and I think we should think about both of them. So again, I'm going to go ahead and draw a second copy of this guy, because we're going to look at two different alternatives. If you remember here, right, this fxy xy could have been gotten either by doing a dx dy or doing a dy dx. We can interchange whether we want to integrate x first or y first. So we're going to look at both cases and see how they look. So I'm going to go ahead and redraw this shape in here. We still have that region of support that is triangular. We're looking at some point on the interior of this guy. The CDF says, hey, look down below and look to the left of this guy. And then if we look at what part of that intersects with where we have non-zero probability, we get this little green shaded area, something like that. Either way that I end up doing the integration, I should get the same results. I probably won't go through the details on both integrals, but I would like to set up portions versions of them so we could get an idea of what our design choices might be. So in this particular case, I think what I would like to do is I would like to go ahead and do this first one as a du dv, and this next one is going to be a dv and a du. And I want to think a little bit about what this means. We had used u and v as dummy variables, right? Dummy variables of integration, just so we don't get confused when we have the actual x and y's, which they will likely be, that will show up in our limits of integration. So u is on the horizontal, right? That's our horizontal, and v is on our vertical, something like that. And when we go to the second case, we're doing the vertical stuff first, the vertical variable first, and then the horizontal after that, something along those lines. So let's think about this first case where I said let's do the horizontal first and then the vertical. If I'm doing things horizontally first, that means I'm building up a horizontal line and then I'm stacking up those horizontal lines to achieve the vertical part of that integration. So I'm doing horizontal first, that's going to build up a little horizontal line, and then I stack those horizontal lines to get my vertical. So you might visualize this as far as an integration as me doing build little horizontal line, 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 right? And then stack all of those horizontal lines together. Okay, so that's the way that the integration would go, doing a du dv. If I go to the second case where I've got a dv du, I'm doing my differential element in the vertical first. That means I'm going to build a vertical line first, and then I'm going to stack those vertical lines horizontally. So in this particular case, I build this vertical line, and I build this vertical line, and I build this vertical line, and then I stack them all across in the horizontal direction to get that same trapezoidal shape. Two different ways of getting the area that is shown here in green. I will say, though, that one of these two methods is absolutely more difficult than the other. Which one is it? Which one is more difficult? Well, I'm going to suggest that this one up at the top is tougher, that this is a tougher way to do it, and that the second one down here is easier. How do I come up with that statement? Let's take a look at the tougher case. If I'm building things up horizontally first and then vertically over here, look at how I build these lines first. When I work down here at the origin and I start building up these lines, those lines for a while go from what? They go from this leftmost axis, right? And then they go to this triangular, this kind of triangular edge on the one side. So I keep building those guys up until I hit that point, right? Until I hit the point where we reach point X, right? This is point X, and this guy was over here Y, because we were trying to find fxy of little x and little y. This point right here is little x, little y, something like that. So once I get up high enough, right, so that I hit this piece, now my logic for finding those little line segments is different. Instead of going 0 to the definition of that angled line, I'm going to go 0 to a fixed value x equaling, or in this case u, that's my variable of integration, u equaling x. So this is going to require two pieces for my integral. This single expression here, right, would have to be done in two pieces because of the way that the logic changes right there when I go from being bounded on the right by the diagonal line to above that when I'm being bounded on the right by u equaling x. I don't want to have to do two pieces for this integral. If I look at it for the other case, what do? I always go from that line up until I hit this upper line, which is what? It's v equaling y, and I do that every single time, and that logic never changes over the entire trapezoid. So I can do it with a single double integral. It's still a double integral, but a single double integral expression. I don't have to come up with crazy logic. I don't have to come up with two different pieces. It is just an easier way to carry it out. Now, if you did it if you did it with these two pieces and you set everything up right, you'll get the same answer. You can get the correct answer that way. You just have to work harder. So let's work on this easier way and make sure that we understand how to set up the limits of integration and then how we carry out that limit of integration as well. So I'm doing things on the vertical first, right? So I'm doing my dv. So I'm looking at how I'm building my y values. If I look the lower limit of this line, so going from point here and then working my way up, so I'm just picking a particular line here that I'm showing. This lower limit is what? It's bound by this triangular edge here, which we knew is what? Y equaling 2x. Now, is a variable of integration, right? As we move along, we know that y, right, we called v, something along those lines. And so I need to be able to handle that particular value. I need to be able to handle that guy. And it's going to come up to a value of y equaling what? This upper line. This thing is fixed for a particular value. Remember, this guy is x comma y. This is an upper line, right? The upper edge, the upper limit is always going to be y in this case. So I do get an upper limit of y. That's fixed. But as I move along here, my little vertical lines, right, their starting point varies, and that's based on the variable of integration, and it is a value in this particular case y. Y we know is equal to 2x, but if I put that in terms of u and v, that's v equaling 2u. So I'm looking for a value 2u. Why do I put in 2u? Because the next integration is with respect to u. Okay, so I'm going to be 2u to y. And then what am I making x go over? I've got to stack all of those little vertical lines together. It goes 0 to x. So my other limit here is 0 to x. Hopefully this is something that's ringing some bells with you. You should have seen this in probably like Calc 3 multivariate calc, where you were dealing with multiple integrals coming together and how you cover regions in a multivariable space. So in this particular case, my integral limits go to u to y and then 0 to x. Really important that you be able to get these limits of integrations right. And for me, at least, the best way of being able to do that is drawing some sketches to help you out as well. Now that I've got it set up, it becomes a trivial type of operation. I'm going to handle the integral on the inside first. I'm integrating a constant, so leave the outside integral alone. That's going to be 0 to x. The inside integral with respect to v, right, is going to be, well, if I integrate 1 with respect to v, that just gives me a v. And I'm going to evaluate, on the limits here. The limits were 2u to y, and then I still will have a du left to do later. So go ahead and plug those values in. So I'm going to get still an integral 0 to x. And when v takes those limits of integration, in this particular case, we are going to get a y minus 2u, and then we still need to do my du. That is a simple integration. That's a polynomial integration. So integrating y du is going to give me a yu, and giving my next piece in there, integral of sum is the sum of the integrals. I'm going to get a minus 2. Integral of u du is going to be a u squared by 2. And then this whole thing has to be integrated on the limits, not 0 to 2, but 0 to x. Something like that. And what do I get out of this? When I put in the upper limit x, I'm going to get a yx minus, the 2's cancel, and I'm just going to get an x squared. And then I'm going to subtract out and evaluate at the lower limit 0, but both of those terms disappear. So y times 0 minus 2, 0 squared over 2 is all 0. So my final expression for this region is yx minus x squared. And that, remember, was my fxy little xy. Just a comment here, it's not a surprise. We were expecting something that comes out and is a function of x and y. You will almost always, just as a point of observation, you almost always see your dependence on the variables x and y show up in things like the limits of integration, right? And you almost always want to employ, as a result, a different notation for how you integrate along the horizontal and vertical. Otherwise, you're going to be confounding your variables. If you did this as a dx, dy, that would mess up with these hardened limits of integration, and you'd end up with a mess. So definitely use these dummy variables of integration. I suggest u and v, something like that. So that is region 2. Oh my, I hope it gets better as we go along. Actually, that one was probably one of the more difficult ones, but let's see what we can do for the remaining ones. Third one, if you think about where we are, we've handled everything in quadrants 2, 3, and 4, and then we've included just this little tiny piece that is that triangular area. I still have quite a bit left to figure out. Let's redraw what this space looked like. So I'm going to go ahead and draw this in again. So 1 and then 1 and 2. I'm going to go ahead and put my triangular piece in there. If you remember, I'm going to just do this in kind of a red sketch. We've already done this stuff off here, quadrants 2, 3, and 4, right? And then just with this last one we did all this stuff on the interior. We still have a bunch of white space to get to. Well, I think for this next region, what I'm going to do in this particular case is I'm going to look at the condition of 0 less than or equal to y less than or equal to 2x, and that I'm going to have 0 less than or equal to y less than or equal to 2. What does this describe for me? If I take a look at this particular case and I say y is between 0 and 2, I know that that's going to say that I've got something in this horizontally oriented strip, right? This part here is 0 less than equal y less than equal to 2, something like that. And then I'm going to say, well, I also need 0 less than or equal to y less than or equal to 2x, something along those lines. That basically just puts me off to the right, and I'm going to do it again as a green. It puts me off to the right here. When I look at y being less than or equal to 2x, we are going to be just looking off over here to the right in this particular piece. So I'm going to be handling now all this space over here. That's getting me closer. I'm going to still have the stuff above that I need to deal with. That's going to be regions 4 and 5. But right now I'm filling in this part here that's going to be this green space. Let's go ahead and take a reflective or an example point in here. So I'm going to pick some point x comma y, and the CDF would say what? Look everything below and look everything to the left. And when we think about where that intersects with the non-zero probability density function, I get this little space in here, something like that. This is fundamentally different, which is why it's a different region than before. Before we had what? Before we had trapezoids that we were dealing with. Now we're getting this little triangular piece, right? And so the integrations are going to look different. And since we need a different looking form of the integration, we're going to need this different region. So let's go ahead and see if we can do that. This one's actually not so bad. fxy little xy is equal to, it's still a double integral, right? We're still integrating some area in the complex plane. It is still a 1 in this particular case. And I don't think it hugely matters. And so maybe this is a good place where we can demonstrate that order of variable integration doesn't really matter. I can do the horizontal and vertical, or I could do the vertical and the horizontal. So let's show it first as a du dv. So that's going to be me doing what? The du says the horizontal first and then the vertical. So I'm going to stack up little differential elements horizontally first. That creates what? Horizontal lines. So I'm going to be doing something like this. Going to get a little horizontal line in there, and then I'm going to stack all those horizontal lines up until I get that triangular piece, right? That's going to be a y going from 0 to y. So I know the outside limits are 0 to y. Now the inside limits, I'm going to always be going from this x equaling 0 point, right, over to the edge of this line. We had already made that calculation. We knew that y is equal to 2x, but we're doing this in terms of because those values are changing as we go through the integration. Let's put it in terms of the variable of integration, the u and v. So that's a v equaling 2u. I am integrating the u first. So let's express this condition of the line. This condition is of this line, right? In terms of the value u. U equals v by 2. So I'm going to be taking my x values from 0 to v by 2, right? It depends on which of those horizontal line stacks I'm interested in to know how far over to the edge I'm doing, right? If I have a value v that started out at 0, right, I'm going to be doing a horizontal line that's going pretty close 0 to 0. That's down here at this little apex or this little tip of the guy. If I picked a value v that was closer to the value y, right, then I would be going somewhere on x that's going to be closer to 0 to y by 2. That's going to be something up here, 0 to y by 2, something along those lines. So that length, right, that length has to change depending on which of the vertical stack I'm in, which is why it shows up as a v in there. Okay, I've got the integral set up here. Let's do the inner one first. So that's a outer integral still staying 0 to y. I'm integrating a constant with respect to u. That just gives me a u. I'm going to do that on limit 0 to v by 2, and then I still have my dv. That's going to be an integral 0 to y, and I'm going to go ahead and put that in. That's v, not v squared, but a v by 2, right? Minus, in this particular case, 0, so it just stays a v by 2 dv. Integrating a v by 2. I wish this thing would just let me do this. Integrating v, that's going to be a v squared by 2, so I'm going to get a v squared by 4, going 0 to y. Go ahead and plug those in. I get y squared by 4. So in this particular case, for region 3, we might call that guy, right? My fxy of little xy is equal to y squared by, whoops, not 2, but by 4. I want to think a little bit about this. We know that we're finding the CDF. It can be a function of both x and y. And what we get here is just something that is a function of y. And I want to make sure that that makes some sense to me. Take a look at this point that I'm at over here. I'm trying to find out what the accumulated probability is here. I'm at a point in x, right, where I've passed any possibility of x doing anything interesting between 0 and 1 or whatever, this edge of line. So there's nothing over here where x can come into play because I'm already past that point of x. But I'm in the middle, right, of where y can have stuff happen. And that's why over here, this green area, we end up getting something that is going to be a function of y, but not of x. We've already passed where x comes into play, but we're in the middle of where y came into play. Now, my next region, you might guess what it's going to look like. Let's just quickly sketch it up here. We'll resketch it in down below. But if I take a look at this guy, we're probably going to do something like this. We're going to look right above that triangle. Now, in this particular case, right, if I look at some particular point in there, we would expect in this case that we're already above where y does any of its stuff, right? But we're in that middle of where x can do things. So I'm expecting the CDF for the point here in this, what we're going to call fourth region, to be a function only of x. We'll see how that works out. Let's try it out. So let's go on down and get down to my region 4. Region 4, we're going to do that above space in there, something like that. This is going to be for y greater than 2, and we could say 0 less than or equal to x less than or equal to 1. I'm going to go ahead and sketch that out, make sure I've got a sense for what this looks like. And we will make sure that we know where we're looking. So we're going to look at the xy plane again, and I'm going to come over 1 full unit in x. I'm going to go up 1, 2 units in y, make sure that I still know where that region of support is for my stuff. And I'm again going to very lightly sketch in red here. First region, right, was quadrants 2, 3, 4. And so we had handled all that. Region 2 that we talked about, right, was the interior of that triangle. So we've handled that. Region 3, right, was everything off to the right of that triangle. So that was our region 3, something in there like that. So I might do this region 2, right? This is region 3. This was region 1, something like that. We're still trying to cover the entire XY plane. That's the CDF has to be defined for the entire XY plane. Now, though, we are interested in what? Y greater than 2. So that's everything above this y equaling 2 line. But it also said x has to be between 0 and 1. So we're looking at this space that's all above the triangle. That's where we're trying to find the CDF values in this particular case. Let's go ahead and pick a point of interest, anything that would fit in there. And again, the CDF says look down, right, and look to the left of that guy, and then go ahead and find out what the accumulated probability is. We have to look at where that CDF region intersects with the non-zero values of our probability density function. And again, what we see here is we get this space, and I probably should have, again, I'm going to go back out of there. Maybe I shouldn't have done this other one as green, but I can fix that. We'll just make make this other part blue, right? The part that's going to contribute to the probability here, right, can only be where the probability density function is non-zero. That's in the triangle, and where the CDF values intersect with that. We get a trapezoid again, right? But it's a trapezoid who doesn't have the one vertex of its point inside the triangle. So it's a little different than region 2. I'll let you do some looking afterwards to see how it's not quite the same as region 2. But because it's a trapezoid, again, I think that there is definitely an order of integration that's preferable. Can you figure out, or can you guess which order of integration is preferable? It should be the same preferable order of integration we had before, because the trapezoid is still oriented in that way. We want something that does not have to be evaluated with multiple double integrals. We'd like to just do it with a single case. Can't always do that, but we can in this case. And so what I'm going to notice here is that if I build my strips vertically first, they always follow that line, right, up to a value y equaling 2. And then we would just stack from 0 to, remember this point over here is just x comma y, so it'd be going 0 to x. So I want to do the y's first. We're integrating 1. That's just the probability density function. Doing the y's first, so that's my dv variable, and then I'm going to do my x's second. The x values are going over this part, right? That's 0 to x, so my outer limits are 0 to x. And then my other ones have to go from this line. What is that line in there? We knew that line was 2x equaling y. If I put that in terms of the variables of integration, u and v, I get 2u equaling v, right? And I am integrating here v, so I would express it in terms of what v is. It's 2u, so 2u up until what? The upper part of that line ends up hitting a hard value of y equaling 2, so the upper limit here is 2. If it's been a while or you're a little rusty in your multivariate calc, you might have to spend some time, and I really would encourage you to do these pictures. They absolutely can help, and you do have to spend a little time and just make sure you get it right. Setup is everything here. Once I've got the setup, the math actually becomes quite easy. In this first one, I'm going to leave the outside integral alone, so that's 0 to x. Integrate the middle. 1 dv is just going to be v, so I get v on the limits 2u to 2, and I'm left with a du. That's going to be an integral 0 to x, and I'm going to get a 2 minus 2u, and then that's going to be a du. And if I go ahead and carry that out, I'm going to get what? A 2u minus u squared going 0 to x. And if I plug in all those values there, I get a 2x minus x squared, and I'm done. And oh, by the way, nice, right? If you take a look at that answer, it's only a function of x, as we predicted based on some of our intuition before. One more region, and unfortunately it's an easy one. I bet we're all kind of getting tired here in this particular case. So region 5, what does it look like? Let me just sketch it out. We don't have to do a lot of math on this. Just a reminder of everything that we've done. So I'm going to go ahead and put my triangle in here. I know that triangle comes out 1 in x and it comes up 2 in y, so I have my x and y in here. And let's go ahead and sketch in what we've done so far. So I'm going to do this sort of light red, right? That was region 1. We've covered already. We've found out what the CDF looks for that. That was this, whoops, let's undo that and just put it in here, and we'll change that color to red. And we know that that was our first region, something like that. We also did the interior of the triangle, something like that. Let me try to make this something more like this. So interior of that triangle, right? That interior of that triangle was region 2. We also had over here, right, everything to the right. And I'm going to just draw that a little differently. So we took care of all that stuff over there. That was region 3. And then we also know that we took care of this stuff above the triangle. And let's just make that as a bunch of kind of horizontally lines. That was my region 4. What have I got left? Not much. I've only got this piece that is both above and to the right of the upper rightmost point of my region of support. So I'm now looking at being over here in this last piece, and let's just pick a reflective point in there. So I'm going to go ahead and pick a pick a value of xy that's in this new region. How would I describe that region, by the way? Easy, right? This particular region up there says any y greater than 2 and any x greater than 1. So my condition here for region 5 is y greater than 2 and x greater than 1. That's the description of this guy. If I take a look at what the CDF says, it says look down and look to the left, and guess what? It includes that entire region of support of the probability density function. This is easy. Fxy of xy is equal to 1. We've accumulated everything. We are really, really close here. I know it's getting to be a little bit of a long lecture. Let's just make sure that we clean this all up. So as a final result, let's pull all the pieces together so I can write a single expression for this particular CDF. I'm going to have 5 regions, so I'm going to need 5 lines to describe my CDF. The first one I would say was region 1, that's 0, and we knew that was for x less than 0 or y less than 0. My next region gave me an output yx minus x squared, and that was for 0 less than or equal to 2x was less than or equal to y was less than or equal to 2. That was the interior of the triangle, right, where all the action kind of was. We had a y squared by 4, and that was for what? 0 less than or equal to y less than 2x. And we needed in that a 0 less than equal to y less than or equal to 2. That was to the right of the triangle. We had a 2x minus x squared, and that was for y greater than, not 0, but 2, y greater than 2 in this particular case. And we also needed in there 0 less than or equal to x less than or equal to 1. So that was above the triangle. And then the last one, we just got a value of 1. And that was the otherwise you could put in here, but I'm just going to write it as y greater than 2 and x greater than 1. That's my final answer. So let's go ahead and mark that off in another color or something like that. My overall expression. As you can imagine, so I'm going to need about probably 5 minutes to finish this example out. As you can imagine, it's really easy to make mistakes in these kinds of guys, right? It's really easy to mess up a limit of integration or confuse a variable or put in something wrong. And when you do that, you obviously are going to get an incorrect answer. I could stare at this guy all day long. I could stare at that expression and not have a good sense as to whether or not this particular set of calculations was correct. But I want to think a little bit about what we looked at before when we did CDFs of continuous random variables. We knew that they started at 0 and ended at 1, that they were non-decreasing functions. So as you moved larger in a variable, they should have never gotten smaller. They should always get bigger or stay the same. We knew that if it was not a mixed random variable case, but just a pure continuous random variable case, that the increase was smooth. It shouldn't jump anywhere. So here's what I would like to do. I would like to plot this in a 3D plot, right? So I will have, in this particular case, my XY plane. So I'd have X and Y, something like that. And then in the vertical, I'm going to do that CDF value. And what I hope in that 3D plot is that I'm going to see a surface, right? That is, I increase either X or I increase Y, right? That this thing will never decrease, so it's always going to be increasing, right? That it would plateau out at 1, right? As I get large in both X and Y, I should come out to that final total probability of 100%. If I look off to the very small values of X and Y off there to the lower left, it should start out at a 0, and I should never see jump discontinuities. Well, I've already done this, and I'm going to open up a different application in this particular case to show those. This first plot is a contour plot, so it tells me lines of constant probability in this case as a function of the variables X and Y. So I have X here going in the horizontal and Y going in the vertical, and my contour plots tell me lines of constant probability. The lines that I've picked in this particular case are each separated by 10%. So this first set of lines in here is probability 0, right? And so I get probability 0 going kind of where I would have expected. That's not such a great line, but you get the general idea. The next one, this is a line of 10% probability, and then a line of 20% probability, and 30% probability, and 40, 50, 60, 70, 80, 90, and then 100% probability. One of the things we'll notice with this, if you're a hiker, these are like contour maps that you might use for figuring out the best way to take a hike. This contour plot has smooth contours. That makes me happy. It tells me that, especially on these boundaries. So we had a boundary here, we had a boundary here, we had a boundary here. Over here was what, region 1. This guy was my region 2. Here was my region 3, region 4, and region 5. If I had screwed up region 3, for example, I wouldn't expect that maybe these transitions would all look nice and smooth, right? If I'd screwed up region 3, it's very likely that something would have broke there and I would have seen something jump and do something crazy. The fact that I've got smoothness across all of these transitions, across all these boundaries, makes me think that I've got my math right. This contour plot is fine. It doesn't help us maybe see that this one up here was 100%, right? And that down here was 0%. You'd have to do some more investigation. But I can, for example, plot this out in a 3D plot like this. This is the same information as that contour plot, just shown where the height is coming out of a third dimension. So I have X now here in one of my two kind of base directions, my Y going in the other, so that's the flat part of this surface, and then the CDF comes out in the vertical. And again, what I see here is something that as I go out to a large negative value, I have a low value that is near 0. If I come out here to a large positive value, right, I come out to a value of 1. And no matter how I go, if I'm always increasing in X and Y, the values that I would be getting as I go along there keep getting bigger and bigger and bigger because the CDF is non-decreasing. Everything follows smooth patterns, regardless of where I'm at in that original triangular kind of shape, underlying projection of that underlying triangular shape. Everything's smooth. That smoothness, that non-decreasing nature of the 3D plot gives me great confirmation that I've got my calculations right. I really think that you would want to be taking a look at stuff like this similar. Well, that's certainly enough for this lecture. We'll pick up on some more examples next time.